Hello and welcome back to HK Academy. Imagine you design a peak current mode controlled buck converter. The crossover frequency is exactly where you want it. The phase margin is around 70 degrees. The output voltage is perfectly regulated. Everything appears stable. But then you slightly change the operating point, and suddenly the inductor current starts oscillating from one switching cycle to the next. How is that possible? In this video, I will show you one of the most important phenomena in peak current mode control, subharmonic oscillations, and why they typically appear when the duty cycle exceeds approximately 50%. Let me show you something interesting. This is a closed-loop peak current mode controlled buck converter operating under load transient conditions. At first glance, everything appears to be working correctly. The converter starts successfully. The output voltage reaches the desired operating point of approximately 3.3 volts. And even when load transients are applied, the converter continues regulating the output voltage. So far, nothing seems unusual. However, if we look more carefully at the output voltage waveform, we can already notice that something has changed. The average output voltage remains close to the desired value, but an additional oscillatory component is now visible. The output voltage is no longer as clean as we would normally expect from a well-behaved converter. The effect becomes even more obvious when we examine the inductor current. Instead of a clean and repetitive switching waveform, the current now exhibits significant cycle-to-cycle variation. The waveform appears irregular and noticeably different from what we normally expect in stable operation. This immediately raises an important question. If the converter still regulates the output voltage, why does the inductor current look like this? And where do these additional oscillations come from? Before answering that question, let us first look at the converter used in this demonstration. Before we investigate the waveforms in more detail, let me briefly show you the converter used in this demonstration. This is a synchronous buck converter operating under peak current mode control. The switching frequency is 200 kHz. The voltage loop uses a Type 2 compensator designed for approximately 2 kHz crossover frequency and about 70 degrees of phase margin. Throughout this video, the controller remains exactly the same. The compensator remains exactly the same. The switching frequency remains exactly the same. In fact, the only thing we will change is the operating point of the converter. And that single change will be enough to produce the unusual behavior we observed in the previous slide. Let us first examine an operating condition where the converter remains below a duty cycle of 50%. In this example, the converter operates from a 9-volt input while regulating a 3.3-volt output. As a result, the duty cycle remains well below 50%. If we look at the output voltage waveform, we can see that the converter responds correctly to the load transient. The output voltage experiences a temporary undershoot, followed by a smooth recovery back to the desired operating point. Now let us examine the inductor current. The current increases as expected during the load transient and then settles to its new steady-state value. Most importantly, the switching behavior appears completely regular. The ripple pattern remains repetitive from one switching cycle to the next, and there is no indication of any unusual cycle-by-cycle behavior. Based on these waveforms, everything appears perfectly normal. This is exactly the type of behavior we would expect from a stable peak current mode controlled converter. Now, let us move to a different operating condition and see what changes. For the second experiment, we keep exactly the same converter. The compensator remains unchanged, the crossover frequency remains unchanged, the phase margin remains unchanged, and the switching frequency also remains unchanged. The only thing we change is the operating point. Instead of operating from 9 volts, the converter now operates from a lower input voltage equal to 5 volt, forcing the duty cycle above approximately 50%. At first glance, the converter still appears functional. The output voltage remains regulated around the desired 3.3 volt operating point, and the converter continues responding to the load transient. However, if we compare these waveforms with the previous case, several differences immediately become visible. The output voltage ripple is noticeably larger. and the inductor current waveform no longer appears as clean and repetitive as before. The switching behavior now seems much more irregular. At this scale, it is difficult to determine exactly what is happening. However, it is already clear that something has changed inside the peak current mode modulator. To understand what is happening, we need to zoom in and examine the switching cycles individually. Let us now zoom into the switching waveforms. The behavior becomes much easier to observe. At the top, we can see the compensator output together with the sensed current signal. In the middle, we can see the PWM signal generated by the peak current mode modulator. And at the bottom, we can see the corresponding inductor current waveform. Notice that the compensator output remains relatively smooth and slowly varying. The voltage loop itself does not appear unstable. The current comparator also continues performing its intended function. The sensed current still intersect the commanded current reference, and the PWM pulse is terminated accordingly. However, if we look carefully at the PWM waveform, we can immediately see that consecutive switching cycles are no longer identical. One PWM pulse becomes longer, the next PWM pulse becomes shorter, then the pattern repeats again. This repeating cycle-by-cycle variation is the characteristic signature of subharmonic oscillation. The converter still regulates the output voltage, but the switching process itself is no longer behaving in a repetitive and predictable manner. The natural question is, why does this phenomenon suddenly appear when the duty cycle exceeds approximately 50%? This is exactly the question we will answer in the upcoming videos, where we will investigate the physical origin of subharmonic oscillation in peak current mode control. Before concluding, let us summarize the key observations from this experiment. The converter continues regulating the output voltage. The voltage loop remains operational. The crossover frequency has not changed. The phase margin has not changed. The compensator has not changed. Yet, once the duty cycle exceeds approximately 50%, a new phenomenon appears. The switching cycles are no longer identical, and the converter begins exhibiting cycle-by-cycle oscillations. Most importantly, this behavior is not predicted by the simplified peak current mode model. This immediately suggests that an additional mechanism is present inside the peak current mode modulator. So far, we have only observed the phenomenon. We have seen that once the duty cycle exceeds approximately 50%, the converter begins exhibiting cycle-by-cycle oscillations. However, we still have not explained where these oscillations actually come from. Why do consecutive switching cycles suddenly becomes different? Why does a small variation in the inductor current persists instead of disappearing? And why is this behavior completely absent from the simplified small signal model? To answer these questions, we must look inside the peak current mode modulator itself. More specifically, we need to examine what happens when a small perturbation is introduced into the inductor current waveform and how that perturbation propagates from one switching cycle to the next. This turns out to be the key to understanding the origin of subharmonic oscillations in peak current mode control. In the upcoming videos, we will investigate this mechanism in detail and show how it ultimately leads to the oscillatory behavior observed in this lesson. If you would like to explore peak current mode control yourself, I have made several free resources available on HK Academy. These resources include LTspice simulation models, control-oriented converter examples, and GNU Octave scripts that can help you better understand the behavior of peak current mode controlled converters. You can download the models, modify the operating conditions, change the converter parameters, and investigate how the system behaves under different scenarios. For example, you can repeat the experiment shown in this video and observe how the converter transitions from normal operation to subharmonic oscillation as the duty cycle increases. I strongly encourage you to experiment with the models yourself. Hands-on simulations is often one of the fastest ways to build intuition for power electronics and control systems. In addition to these free resources, I am currently developing a comprehensive course dedicated to digital peak current mode control of buck converters. The course covers the complete engineering workflow, including peak current mode fundamentals, small signal modeling, type 2 compensator design, subharmonic oscillations, slope compensation, digital implementation, and practical verification using simulation and real hardware. You can find all resources and future course updates on HK Academy. Thank you for watching, and I will see you in the next video.